Hi class, I wanted to talk a little bit about interpreting weather maps and air pressure charts. And we're going to start off looking at just surface weather maps. And so there are a few rules that we want to keep in mind as we are looking at these surface weather maps and interpreting them. And the first is that if we have a surface low pressure, we can interpret that the weather is probably going to be cloudy and there's going to be precipitation. And remember that cyclonic flow, which in the northern hemisphere is in the counterclockwise direction. And if we have a surface high pressure area, then we're going to have more clear and fair weather, and that is going to be anticyclonic flow in the clockwise direction in the northern hemisphere. In the southern hemisphere, and an anticyclone is in the counterclockwise direction. If we have a steep surface pressure gradient, that means the isobars are close together, then the winds are going to be stronger and more powerful. If those isobars are further apart, then we have a mild surface pressure gradient and the winds are weaker. Our surface winds flow from high pressure to low pressure, but remember there is the Coriolis effect as well as the frictional effect with the interaction of the air with the surface of the earth, and so therefore the winds are not going to flow directly from high pressure to low pressure, but they're actually going to cross the isobars at an angle. And in the northern hemisphere they're deflected to the right, and in the southern hemisphere they're deflected to the left because of the Coriolis effect. So let's have a look at a surface weather map. This is a really simplified one from a textbook where we have a high pressure system here over the northwestern United States and a low pressure system here over the southeastern United States. So first thing we want to notice are these lines. These black lines are what we call isobars. So those are lines of equal air pressure at the surface. And these air pressure lines have now been normalized for elevation. For example, here in Colorado, of course, we're at higher elevation, but what they're doing is they're saying, okay, what would the pressure be at sea level? So they've removed the effect of elevation. So the isobars represent lines connecting points of equal air pressure at the surface at sea level, and higher number here means higher air pressure, and a lower number here means lower air pressure. And so we know that air is going to move from high pressure to low pressure. And if we have closed isobars, like a closed polygon, a closed circle, then we know that's sort of like a peak. It's just like a topographic map. Same concept if you're looking at a topo map. So we have this high pressure here. In this example, our pressure is 1,020 millibars. And we can see as we go to the south, the air pressure is going to decrease until we hit what we're calling a trough, which is basically just a linear low pressure area. And then notice the air pressure increases again. So it's like a valley. So we head down into this pressure valley and then up to this high pressure peak. Let's go to the east. So we're going to decrease from 1,020 millibars of pressure to a low of less than 1,008 millibars. And in this case, this is actually what we call a ridge, because if we head in this direction, we're going to head south down into this low of 996. So see, the air pressure here is higher, and the air pressure here is lower. So in this ridge, the air pressure actually is just above 1,008. Now, and then if we go this way, we go down again. So this would be like a ridge line heading down to a low. So what this tells us is that we would expect there to be cloudy, potentially rainy weather down here in the southeastern U.S. and fair, clear weather up here in the northwestern U.S. where we have high. And then in this high pressure ridge, probably more fair weather, and in this low pressure trough, probably more cloudy precipitation. Now, if we move into the upper level winds, things are a little bit different. Do you remember we talked about geostrophic winds? And in the upper level winds, the frictional force of the wind flowing over the Earth's surface doesn't have an effect on the winds anymore. So what we have is just that pressure gradient force and the Coriolis effect, which in the northern hemisphere is going to force that wind to the right. And what we end up with then are winds that follow our isobars. So notice these the wind barbs. We know the direction of the wind is from the side of the barb that has the flag to the side that doesn't have the flag. So basically this is telling us that the wind is paralleling these isobars, which is exactly what we'd expect in an upper level wind chart. And now an upper level wind chart is presented a little bit differently than a surface level air pressure chart. what's happening here is that they're telling us at what elevation do we reach 500 millibars of pressure. And the idea is that 500 millibars is halfway up in the atmosphere. So we're at about 1,013 at the surface, and 0 at space. 500 millibars is halfway up. And so what we're saying is that the elevation of that 500 millibar level will vary a little bit. If we have cold air, where's that 500 millibar level going to be? It's going to be further down because that air is more dense. So that column of air is squished, so that 500 millibar level goes down. If we have warm air, that 500 millibar level goes up. And because that air the warmer air is less dense, it expands, and so the 500 millibar level is at a higher elevation. So we can see here we go from low elevation to high, and so that means we'd be going from cold temperature to warm temperature here. And then over here we have 5480, so this is a lower elevation for the 500 millibar, so we would expect there to be lower temperatures here in this region over Ohio and Indiana and Kentucky. And so we're going from warm temperature to low temperature, from 500 millibar level that's higher elevation to 500 millibar level that's lower elevation. Now on these charts we also are showing isotherms as the dotted red line, so those lines connecting points of equal temperature, and we can actually see minus 25, and this is temperature at the 500 millibar level, so this is high in the atmosphere. So minus 25 degrees C. Here in this colder area here, and we can see the temperature increases. We're at minus 15 here, minus 10. So temperature is increasing as that 500 millibar elevation is also increasing. So our wind barbs are telling us the direction of those upper level winds at the 500 millibar level. The type of flags on the barb are telling us about the wind speed, and the angle of the barb is telling us which direction the wind is flowing. So just a reminder, remember we talked about how a warm air column, that less dense air is going to spread out, and so that 500 millibar level is going to be higher with cold air, and the cold air squishes down, and so that 500 millibar level is lower if we have a column of cold air. So if the 500 millibar elevation on an upper level chart is lower, we would expect the temperature to be colder, right? Okay, so let's look at a real surface weather map. This is from Thursday, July 11th, and what we see are these dark maroon or red lines are giving us our isobars. Those are the lines connecting equal pressure, and this is in millibars. So we have high, we go from 1024, there's a 4 millibar interval between lines. We go from 1024 down to some lows here. We go up to a couple of highs. There's a big high pressure system sitting over Minnesota, Iowa, and Wisconsin here with a pressure of 1,020 millibars, and then we decrease into a low. This is a trough. Right here, this big dashed line right here is telling us that's a low pressure trough, and then we head up to another high pressure over the Atlantic Ocean. And then we can look at the same day, at the same time, our upper level pressure map. It's a little bit more confusing and hard to read, but our wind barbs again in the upper level 500 millibar height are following our isobars, which is exactly what we'd expect. The number here is telling us the elevation in tens of meters, so we can add a 0. So that's 5,760 meters above mean sea level. And what we're seeing is we have a low right here, so that's going to be colder temperatures. And remember, this is minus 24 degrees Celsius at the 500 millibar height. And we're increasing in temperature down into the southern part of the United States, which is exactly what we'd expect in the middle of July in the summertime in the U.S., right? So I hope that helps you understand the isobar lines and 500 millibar height lines that we have on surface weather maps and upper level charts. So let me know if you have any questions.